Good afternoon, everyone. Thanks for joining us for this webinar. It's the first in a series of webinars. We're going to talk about that and what all is going to be contained in that series. And that's really what the purpose of today's webinar is to introduce you to this MarSurf series of webinars to talk about surface metrology and surface measurement. Many of you I know from seeing who all has registered are quite familiar with Mahr, and so you're aware that Mahr is a global leader in the measurement of surfaces. Some people talk about surface finish, some talk about surface texture, some talk about surface roughness, others just say finish. There's a lot of words for it, but it means basically the texture of a surface. Some people don't like the term surface roughness because you're not intentionally making the surface rough. You're trying to make it with a defined texture or defined finish, so it has a certain functional characteristic. And so many people choose the words like surface texture rather than surface roughness, but all of them are sort of interchangeable. And if you're tuning in, you're probably familiar enough with surface measurement to know that surfaces can be measured in many, many different ways with different kinds of tools. You might do it in different environments and for different reasons. Manufacturing a product, designing a better product. And to that end, you can use all kinds of different parameters that you can calculate from the data measured on the surface. And it's something that our customers often tell us is quite confusing, because there are so many different ways to do it and so many different parameters and so many different tools, and some of them have advantages and disadvantages, and some of them can measure certain parameters and not other parameters. And for all of those reasons, it's something that people frequently tell us is kind of a confusing topic. So to address that, we decided to do not one webinar, but a series of webinars to talk about different aspects of this, like some of the different tools you can use to measure surface roughness, some of the different parameters that you could calculate from the measurements, and how to maybe automate it in a production environment versus get the best performance in a R&D environment or something like that. So that's kind of the purpose behind this. This is episode 1 of a 6-part series. There'll be 5 more. They're coming at a rate of 1 a month over the next 5 months. And we will address topics like the basics of surface measurement. There's a bunch of information, and as I said, a lot of people tell us that things are kind of confusing sometimes, but the foundation of surface measurement is really pretty straightforward. And so we'll talk in the first one about this fundamental way that most people measure surface finish and the fundamental parameters that they're getting from those measurements. And then go on to talk about optical surface measurement. It's a great topic. It's a great new technology, newish technology. Has some pros and cons, offers some abilities that you don't have with more traditional stylus-based instruments. Then we'll talk about, in the third one there, more than just RA. What are some of the other parameters and how do those get calculated, and what might they reveal about the surface, and whether it's good for a certain function or not. Beyond that, we'll go into 3D parameters that tell us something about the 3-dimensional characteristics of a surface. And finally, the last one we'll look at using surface measurement in a production kind of environment at the point of manufacture for a product. So what do I mean when I talk about surface measurement, surface finish, surface texture? This is a cut and paste right out of the standard. When we talk about the irregularities present on a surface, anything from a perfectly flat, perfectly smooth surface is considered an irregularity. And those irregularities come in the form of small things as well as larger things. So if I'm sitting at my desk here like I am today, and I think about taking my thumbnail and kind of just feeling the texture of the desk, that's the small scale stuff. That's the roughness. And at the other end of the spectrum, on the left-hand side of the screen, there is the large scale stuff, the form. If my desk is kind of old and I've put heavy stuff on it for years and it's kind of bowed down in the middle, and so it's kind of got this sag in the middle, kind of this U shape, that's the large scale stuff. That's the form. And in between that, we have things like waviness. So we're going to focus in this discussion, in this whole webinar series, really on the roughness, the stuff all the way to the right end, the smallest of the stuff in the irregularities on the surface. But all of those other irregularities are present there, and we'll allude to them at times through the discussion, but really the focus is on the tiny stuff, the things that we consider surface roughness or surface texture. So how did we get to where we're at in the world of measuring surfaces? Well, it's taken about, since the Industrial Revolution, when people cared about the surface finish of the surfaces they were measuring, till today to get where we're at. And the original way to measure surface finish from 100 years ago or more was literally your thumbnail. That's the title of this series, and that my grandfather 100 years ago, he would have measured a surface finish with his thumbnail. He would have had a box like you see in the lower left-hand corner of the screen there, full of samples, and some people still do this today. And he would have taken his thumbnail and scratched a sample and then scratched the part, and then he would scratch another sample and scratch the part he was machining, and then scratch the next, and try to find the one that is the most similar to the surface he actually is trying to measure. And you see in this box of masters, there's grinding, milling, turning, types of surfaces with different types of surface finish, and that's still in use some places today. Not very common in usage. We don't actually make those kinds of masters. We make instruments to actually measure the finish, but you will see these in machine shops around the world today, still sets of these artifacts to compare the thumbnail test to. Around about the 1920s, it moved to being a microscope-based thing. And in some of those microscopes, you had lines or reticles where you could see sort of the size or scale of things that you were looking at. And it became a little bit more scientific, became a bit of a judgment call as you looked at a surface to say, well, I see kind of a turning pattern on the surface and the peaks look to be spaced out about this much. You didn't have necessarily great idea of the depth of the grooves, but you could sort of see something on the surface, maybe a little bit better than you could feel with your thumbnail. And that became kind of typical. And then the first instruments, which actually took a diamond and moved a diamond across the surface to measure it, started in the 1930s, but didn't become really popular until about the 1950s. In the far right view, you see a scanning electron microscope view of a diamond stylus, and the tip on a diamond stylus that would be used to drag across the surface and measure the motion of that stylus as it follows across the surface, and therefore get a representation of the surface coming from that diamond. The Mahr product line uses a lot of those kind of diamond-based instruments, diamond stylus-based instruments, and is one of the broadest range product lines in the world for the measurement of surface finish. It's really made up of kind of three parts, which I'm going to look at individually. There's the kind of the handheld and portable things in the upper left-hand corner. Then the middle of the screen is kind of the stationary or skidless. We're going to talk about what those words mean, but still typical diamond stylus-based types of instruments. And then across the bottom, you see the optical methods, the optical instruments using interferometry or microscopy to measure surfaces. And so we make quite a wide variety of product that covers all of those different areas. So I'll start with by far the most common types of instruments that people use today. These are the skidded, we'll come back to that in a minute, what skidded means, handheld, portable surface measuring instruments. These are the kind that we sell hundreds of for every 1 or 10 of the others. They typically cost something on the order of a couple $1,000s. You can carry them around in one hand. You can take them with you and measure things wherever you go in the factory or wherever you happen to need to be measuring something. And like I said, they're by far the most common in usage. And they tell you an awful lot about the surface, and they're pretty good at what they do. They do have some limitations, but for the typical measurement of what is my average roughness on this surface, they're very good at that. They do the job quite well. As you go from left to right across the product line there, you see our PocketSurf 4. The PocketSurf was the original handheld mobile device about 30 years ago now. And we're on generation number 4 of that. Then we move up to the PocketSurf 10 or the PS10. Uses the same kind of probe technology as our higher end instruments, but puts it in a package where you have the ability to have a touch screen to operate it on from the top of the device. And finally, our M310, which is related to the PS10, but adds a lot of features and capability. You've got Bluetooth to connect to a printer, or which is there in the picture, or a keyboard. You've got USB to connect to printers or other kinds of devices. You've got input-output for remote control in automated applications. So you've got a lot of capability in the M310, but in this fairly inexpensive, skidded world. Well, what does skidded mean? I keep saying we'll come back to that. So I'm going to talk about skidded versus skidless, which is the next category of devices. So what does skidded mean? The idea behind the skid is if I'm trying to measure this part right over here, this crosshatched skid and the blue diamond are moved across the surface together. The blue diamond moves up and down relative to the skid, which rides across the peaks on the surface. So what I measure when I measure the motion of the blue diamond moving up and down with this pickup back here, I measure the motion of the blue diamond up and down relative to the skid, which is following the basic shape of the surface by moving across the peaks. And that's what skidded means. And the skidded measurement means we can take those handheld devices, we can just set them down on some surface and push the button to measure and let go of it, and it will follow across the surface and take the measurement. That's part of why they're fairly inexpensive and part of why they're so easy to use and so typical and common in use all over the place. And they do a really good job of measuring a lot of the types of profiles and parameters that we're interested in when we're talking about surface texture, surface roughness. But they can't measure everything. So sometimes we also need to do skidless. And what does skidless mean? Skidless means, okay, I've got this part to be measured now. I've got the blue diamond, the same blue diamond, but now it's not moving up and down relative to a skid that's riding on a surface. It's moving up and down relative to this whole system, which is inside the drive unit, which is a datum, a straight guideway, and it measures the stylus moving up and down relative to this flat surface inside here. So now I've got a bigger drive unit, I've got a bigger system. They're typically more expensive, but we have the ability to measure true shape without having to have a skid that follows some contour on the surface of the part to be measured. In the first or the next webinar, we're going to talk a lot more about the skidded and the skidless and spend a lot of time looking at why skidless is so common and so popular and why it's okay for an awful lot of things, but maybe not for a few things. When I look at the measurement I get out of either one of those instruments, I get a direct profile. If I have a skidless instrument, I can see that my profile may be, my drive unit is not aligned perfectly with the surface I'm measuring, and I've got this profile that kind of runs downhill. If I subtract out that downhill portion of it from the data that I have here, I get just my measured profile without needing to level it. It's leveled by subtracting the inclination out. And now if I take that and I say, well, from that I want to know, well, what's the roughness? What's the tiny little stuff? I'm going to filter, which is also a topic we're going to talk about in a couple of the webinar episodes in some detail. How do we filter, and what does it mean to filter, and how do different filters work differently and give you maybe different results. But if I filter out just my roughness, I get a profile of something like this. And what I take out is this waviness profile. And if I'm measuring with a skid, this is the long wavelength, general shape kind of stuff from peak to peak that the skid is kind of following across the surface. And so that's being subtracted out by the skid, or in this case, subtracted out by the filter. And what I'm left with is just the roughness profile. So when I've got just the roughness profile, I've taken out the waviness either with a digital filter or the mechanical filter of the skid riding across the surface, and I've taken out the inclination, which also the skid takes out for me. So the skid kind of does this job for me. So the skidless units, that's the broadest part of the product line. That's kind of the middle of the product line. Starts with also smaller handheld kind of devices and moves up to larger devices with longer probes and more probe range, and even to the point of being able to do form measurements and contour measurements in combination with the surface finish measurements, and at the end allows us to automate the measurements of all of these kinds of surfaces. I'm going to look at each of those in a little more detail. So it starts with something like our MarSurf M400. That's intended to be used either as a portable device or can be used on a measuring stand where you mount the device, the drive to a stand, bring the part to the measuring instrument, set it underneath it, and bring it down into contact and do the measurements. It's got its own dedicated processor, doesn't need a separate PC or anything. It's got this device here, so it can be easily portable, can be carried around, can even be set right on top of a item to be measured out in the factory, just like a skidded system can be. The controller can store the data, can be taken back to a PC and plugged into a PC to get the data onto a PC or into some other system, SPC data collection, something like that. But it's kind of the entry level. It's where we cross over from the portable handheld kind of devices into the skidless devices. Take that one step further and move from the dedicated processor into a software-based solution on a PC. We've got our XR1 software. That's a Windows PC-based Marwin software. It could be portable if we put it on a laptop. Could be pretty much just as portable as this kind of a solution, and gives you all the same kind of typical roughness parameters. Stepping up from that, we would have the GD systems, 140 or 280 millimeters, and that refers to the length of this drive unit here, either 140 or 280 millimeter long travel. So I can take 140 millimeters of measurement all in one measurement. The general purpose drive systems use a probe system that is specifically tailored towards making really good roughness measurements. It's very high resolution, not very big range. In order to get that very high resolution, gives you maybe half a millimeter or a millimeter of measuring range with something like a half a nanometer or a nanometer of resolution within that range. So it's very, very, very tiny in terms of the range, but the resolution, and you can see a lot of detail on the surface and can very well measure the surface roughness. The counterpart to that is the contour drive, and it's kind of the opposite. It has a big range. Instead of a half a millimeter or 1 millimeter, it goes from maybe 40 to 100 millimeters and has micron level kinds of resolution, not nanometer kinds of resolution. It's sub-micron, but it's not anywhere near the sub-nanometer kind of resolution. And it's what allows us to measure more of the bigger form characteristics. If something is supposed to have a radius or a shape to it, we can measure that. If you go from one surface onto an angled surface of a chamfer next to it, and you want to calculate the angle of that between those surfaces and get the chamfer angle, you can do that. The depth of a groove, all of those kinds of contour or shape-based things that we don't typically think about as surface finish because they're not an RA number or a surface finish measurement, but it is part of measuring a surface. We can do that with these contour drives. We can also measure surface finish with these in some limited cases. The really fine polished or ground surfaces, no, it doesn't have the resolution that I need to do that measurement. But for some surfaces, it's fine. It's enough resolution to do what you want to do. Then we go into the combo systems that allow us to do both. Well, we've got the variable drive system, again, 140 or 280 millimeters of total drive length. But it allows us to swap out this probe system that's underneath the drive unit and gives us the option to use either one from the GD or CD and switch back and forth and get the best of both worlds by getting the high resolution, low range for surface roughness, or the high range, giving up a little bit of resolution to get that the contour drive, and all of it comes in one system. Another option to do that is the LD, so-called because it was originally a laser drive system. Today they don't really have a laser in them. They still do have an interferometer, but it's an LED-based interferometer, and they use a probe system that gives you really, truly the best of both worlds. Instead of giving you the 100 millimeters of the contour drive, you get maybe 26 millimeters here, but you get the sub-nanometer resolution through the whole 26 millimeters. The interferometer gives you the incredible resolution while still giving you a big range, so you can measure both the shape, contour, form type characteristics as well as the surface roughness characteristics. And you can even measure surface roughness on things with a lot of shape to them, like a bearing raceway or something like that. Finally, we have the automation kinds of portion. I said some measurements are made in like a manufacturing type of environment. You have high volume, you're trying to measure a lot of parts and measure them as fast and automatically as possible. We have a couple of ways to do that. You can take pretty much any of those skidless systems. We can use our CNC modular, which are some standardized linear axes, rotary axes, combination linear plus rotary in one unit, and build a simple little fixture for some parts that a customer might have, and write a program within our standard software, and we can measure typical characteristics and do the automation job with minimal extra effort. When that's not enough, when the flexibility required is too much, or the complexity of the parts and the number of features to be measured and all that is just too complex, we offer CNC Premium, which allows us to use really all kinds of different sizes and configurations of CNC axes to automate a measurement and turn a part around every which way to get into all the holes and nooks and crannies and grooves, and everywhere you want to get to on the part to measure the surface finish. We can do that with CNC Premium, and we've got some additional special software which allows us to automate those measurements and program that up and create these automated solutions, especially in high volume production kind of environments. And finally, when we talk about production and high volume production, we offer a lot of solutions that do things like this. This is one example out of dozens I could have thrown in here, but these customized solutions basically all have one thing in common. They protect the surface finish measuring device and make sure that it's brought to exactly the right place where you want to make the measurement. Then it comes out of its protection, makes the measurement, goes back inside and allows you to move it to the next location to be measured. So whether it's in crankshaft bores like this device, or cylinder bores or oil bores on an engine block, or different kinds of bores in a transmission housing, or we've built systems to measure small hydraulic components that you put instead of bringing the gauge to the engine block like you do here, you have the gauge stationary in a fixture on the bench top, and you bring the small pistons or cylinders right to the gauge. So all of them they're tailored to match whatever the application is, but they all share in common this idea that they keep the surface finish measurement system safe and protected inside some kind of a housing. Bring your parts to the gauge, or bring the gauge to the part, and then it comes out, takes the measurement, goes back in. Keep making sure you measure where you want to measure, and making sure you keep the gauge from getting broke due to the mishandling in a high volume kind of an environment. And lastly, I'm going to shift gears and talk about the optical surface measurement. Most people I talk to think optical methods are new, they're newfangled, they're fancy. Well, they're relatively new, but they've been developed and gaining popularity over the past 30 years or so. I've been doing this kind of surface measurement for about 30 years, and 30 years ago, people were thinking optical was going to totally replace the tactile within the next 5 to 10 years. Well, it hasn't, and there's some reasons for that, but I think the momentum has picked up in recent years and will continue to pick up, and we're going to see a lot more usage of optical surface measurement in the next 5 years than we did in the last 5 years. So optical methods can work in 2D like the tactile methods, but more typically they work in 3D. It's one of the advantages. So the typical tactile 2D methods, they work well for a lot of surfaces. They work well partially because the manufacturing methods that create those surfaces allow them to work well. So if I have a turned part, a turned shaft, and I take one 2D trace on it, any 2D trace is probably a lot like the next one that I would take if I rotated the part a little bit, because they all got created by a common process. And that's part of why 2D methods work very well for a lot of the typical manufacturing processes. You think turning, grinding, the surfaces are very symmetrical or similar as I go around the part. So the 2D methods typically work quite well. But you know, as engineers, we get smarter every year, and we develop more complex surfaces that are supposed to have certain functional characteristics, and we put coatings on these surfaces to allow them to have certain characteristics, whether they be friction or anti-friction kind of coatings, whether they be wear coatings or whatever they might be. They're probably supposed to have certain three-dimensional characteristics to them to help them do what they're supposed to do. And if the surface has a three-dimensional characteristic that is important to its function, you probably need to be able to measure it three-dimensionally in order to assess whether it is going to perform as you want it to. So the optical methods are ideal for that. There's a lot of different optical methods out there. There's even more than I've got here. At Mahr, we really focus on the first two, the white light interferometry and the confocal microscopy, but there are electron microscopes, there are atomic force microscopes. All of these get into kind of smaller things than we're used to dealing with, and kind of higher resolution, but they're also incredibly expensive and incredibly rare. You find them in a lot of research kind of environments, but not that many manufacturing kinds of environments. So if I look at our optical products start out with the white light interferometers of the WI50 and WI100, and that's really a difference between the range of 50 millimeters plus or minus 50 millimeters in the X and Y of what we can measure, or 100 millimeters in the X and Y of what we can measure here, plus some additional range in the Z to handle what might be bigger parts also in the X and Y. Goes on to our CM series, which is the confocal microscopy series. We have something kind of unique in the mobile device, as well as the Explorer and the Expert, and kind of like over here where you get a bigger stage and bigger Z height with the Expert than you do with the Explorer. We have different steps in the series, and we have different levels of automation. The Expert having the most level of automation. The mobile is unique in that here we put the part to be measured on an XY stage underneath the optics, and the XY stage moves the part so that we can scan around and we can stitch images together and make an image of the surface. We do the opposite with the mobile. We've got an XY stage that moves the optics or the objective above the part around in the X and Y, and allows us to build up a three-dimensional image by stitching images from each individual image together. And finally, when the parts get even bigger, or we want to put a combination of technologies together, or we want to use a couple of other technologies that we've got the Select series. Here you see a gantry style machine. We can have one or more of these kind of sensors that we have over here in this measuring head. It's the same sensors, but we might combine them. We can have even bigger XY stages than the 100 millimeters. We can have up to like 300 millimeter by 300 millimeter stages. And we have the option to add additional sensors besides one of these. We can add a confocal point sensor or a confocal line sensor. So the confocal microscope, or the confocal microscopy kind of approach, is you take an image, and the image is an X, Y, and Z height image. It's one snapshot in time. You get a whole three-dimensional image, whereas the confocal point sensor works a lot more like the tactile systems. It is confocal, but it only measures one point at a time, and you move it across the surface like you move a diamond across the surface to scan over the surface. So it's kind of somewhere in between a tactile method and a confocal method. You get the image built up from the confocal point sensor by taking many, many points as you scan it across the surface. And if you want to do that a little faster and get a 3D image, we make a confocal line sensor system, which has a whole bunch of those confocal point sensors all in one line array, and you move the whole line across the surface at once, sampling all of the point sensors, then moving over, sampling all of the point sensors, moving over a little bit, and you build the 3D image that way, and even faster than by scanning with the point sensor one at a time. All of those things can give you interesting three-dimensional views of a surface. I have a lot of people ask me, so why would I go with the optical? As I mentioned before, you get a 3D image, and if you're looking for 3D characteristics on the surface that are important to the functionality of the surface, you probably need to be able to measure it in 3D. But really, what are the pros and cons of the optical methods? So, big pro, most methods allow you to see a surface in 3D. The confocal point sensor requires some time and effort to do it. You got to scan across the surface. Most of the other ones give you a 3D measurement right out of the box. They're non-contact for delicate surfaces. We deal with a lot of surfaces where people just don't want to touch them. They're worried about touching them. Whether the diamond moving across the surface would really damage the surface or not, whether it would really impact the functional performance of the surface or not. The concern is so great based on the price of the components that are being manufactured, or the processes that are used, that you do not want to touch it. And finally, it's fast because you get the 3D all at once. Well, if it's got pros, it's probably got cons. So what are the cons? Well, most typical ones that people would talk about is there is no optical solution for $2,000 or $3,000 like there is with a skidded tactile surface finish. So it's more expensive. And functionally, the field of view is fairly small, usually a few millimeters by a few millimeters. So you may not be able to measure the same longer wavelength kind of errors that you can with the tactile methods. For a lot of surface roughness characteristics, that's okay, because it's the little stuff we're looking for. But if you need this bigger field of view, you either need to stitch multiple images together, or you need to have a big field of view with one objective, which causes you to lose some lateral resolution. So that is often considered kind of a con or a detractor of them. So with the Mahr use of white light or confocal, which one's better for what? Well, white light has a higher vertical resolution in the Z direction of an XY surface, higher vertical resolution. So it can measure smoother surfaces. What are smoother surfaces? By smoother, I mean like semiconductors, like highly polished mirror type surfaces, like highly polished optical type surfaces. The white light is very good for those kinds of things. It's best for relatively flat surfaces, and it has a residual noise, or meaning if I were to take a perfectly polished optical flat, put it under the system, I'm probably going to get the lowest roughness and lowest flatness number from a white light system of any of the products that we make. The confocal microscope approach is more versatile, can measure surfaces with more form to them, more shape than with white light systems. We can get more of an image back from a surface, even if it has some shape to it. It's quite versatile and doesn't really have a lot of sensitivity to varying reflectivities of surfaces or colors of the surface or the type of material, whether it be plain steel or even plastic or titanium nitride coated steel or something else. It's quite good at adapting to the type of surfaces. You can get great measurements, great agreement and correlation to stylus-based instruments. So the confocal microscope world is kind of the workhorse world of the optical systems that we manufacture and sell, but both are possible. You can see we can get some great three-dimensional views of surfaces, and these are both done with the confocal microscope kind of a solution. That you can see here, there are some structures present that if I measure in one direction versus the other, the surface is going to have very different characteristics. So I probably, if I'm interested in the size and shape of those structures in multiple directions, I probably would really appreciate the ability to measure that in 3D in order to look at those structures. This is a pretty homogeneous surface and not too different from left to right as it is front to back. So on those 3D surfaces, there are 3D parameters, just like there are 2D parameters. RA is the one people know from the skidded and skidless instruments. We're going to talk about parameters in episode 4, and we're going to talk about lots of different parameters. In the 3D world, there are 3D analogies for the 2D counterparts that exist that people are commonly using, like RA and RZ. There's SA and SZ. There's bearing area curve parameters. If you're familiar with bearing area curve, Abbott-Firestone curve kinds of analysis methods. But a lot of these parameters are just kind of three-dimensional mathematical adaptations of what people are used to doing in 2D. And I think generally most people working in the 3D surface finish world would agree that true adoption of the three-dimensional measurement methods will come when the only way to get the parameters you need to ensure the function is 3D measurement. So 3D parameters that only work in 3D, that only tell us what the function of this part is whether this part will function as intended or not in 3D. If you have to do it in 3D, then we'll see widespread adoption of 3D measurements. So that generally concludes our time today. Thanks for your interest in this series. I hope you'll tune in for many of the others. As I said, we will touch on typical surface finish measurement, how we do it, why we do it, what the parameters and filtering are. We'll look in depth at optical surface measurements. We'll look at other parameters besides RA. And in the fourth episode, we'll look at 2D versus 3D parameters. And fifth episode, and finally look at some of our solutions for measuring right in the manufacturing. With that, I'm going to kind of conclude and then see who has any questions, if there are any. Okay, I'm not seeing any questions, so I'm going to, again, thank you for your interest today, participation. Appreciate you tuning in and spending your time, and look forward to seeing you at our futures. Yep, oh, I thought there was a question. No, there. Okay, so thank you again.